Hi everyone, here is the part 3 of our chapter 10. So we're going to learn about ethers and some other functional groups in this section. Alcohols and ethers have similar leaving groups, and you see they have a lot of similarities. Alcohol, you have alkyl group, oxygen and hydrogen, whereas an ether you have two alkyl groups in the sides of the oxygen. So both alcohols and ethers must be activated before the compounds can react. Remember how we activated the alcohol? That we make it a good leaving group, either by making a water molecule or either making a tosylate. Remember, we had to activate it. So similarly, ether also needed to be activated. So OR group, or alkoxide, is a very poor leaving group. So in the presence of an acid, it can protonate. Oxygen can get protonate. Now we have a good leaving group as an alcohol. Good leaving group, ROH. Okay. Now when you heat it up with the iodide, so you can form alkyl iodide, and then the leaving group is alcohol. Reagents such as thionyl chloride, PCl3, tosyl chloride cannot be used to activate ethers, because ethers do not have a proton that must be lost to form a stable product. So mechanism for the ether cleavage, and that will undergo via SN1 process. Cleavage of a ether. So this is the ether. This ether, one side you have a methyl group, and then the other side you have this group. Okay, tertiary butyl group. So in the presence of an acid, oxygen will become protonated. Okay, and then since this side you can create a tertiary carbocation. Once the oxygen get protonated, it can lose this molecule as a methanol group, CH3OH, a neutral, small, stable molecule, methanol, and you form a carbocation. Once the carbocation form, iodide can substitute to the carbocation, forming a tertiary iodide. Okay, so basically we cleaved the ether group. Now the two molecules became methanol and tertiary butyl iodide. If a relatively stable carbocation is formed when alcohol leaves, it will be an SN1 reaction. Mechanism for ether cleavage, if it goes via SN2. Now you have a methyl group on this side, a propyl group on the other side. And this is the oxygen ether. You add acid, ether get protonated, forms a protonated oxygen group here. Okay, and there are two choices. You can form the alcohol from either side. Now you have a nucleophile I-. Nucleophile attacks the less sterically hindered carbon. Now this carbon has 3 hydrogen, whereas this carbon has 2 hydrogens and an ethyl group. So this is sterically less hindered. So the nucleophile become easy to approach from this side. Since it's going to go via SN2 bimolecular substitution reaction, nucleophile I- goes to the less hindered side, and then it leaves the alcohol from the other side. So the two products after the ether is cleaved going to be propanol and methyl iodide. If a relatively stable carbocation is not formed, when alcohol leaves, it will be an SN2 reaction like this. So these ethers they use as common solvents because they react only with hydrogen halides. They are very inactive compared to the alcohols. Alcohols also not that reactive, but compared to alcohols, ethers are less reactive. So we can use them as solvents, common solvents. Another type of ether, which is a cyclic ether, we call it as an epoxide. So how do we synthesize an epoxide? So if you have an alkene react with the peroxy acid. In a peroxy acid, you can see it has a carbonyl group. In a normal carboxylic acid, you will find only one oxygen and then the hydrogen. But the difference in the peroxy acid is now you have two oxygens over here instead of one oxygen. Okay. Alkene in the presence of a peroxy acid. This oxygen insert between the two carbons and form epoxide. You start with the pi bond breaks, and then the two new sigma bonds forms. Whereas this is a carboxylic acid that result from this reaction. So this is a carboxylic acid with one oxygen, whereas a peroxy acid has two oxygens. Epoxide is an ether with a three-membered ring. Synthesis of an epoxide. So how do we synthesize? You can add, so this is an alkene. You can add chlorine and water. And so you will get anti-addition. Chlorine coming towards you, hydroxyl group going away from you. And then when you add sodium hydride, this is a base. Sodium hydride, H minus, grab a proton from hydrogen, OH group over here, form alkoxide. And this oxide attack this carbon and leaves chlorine. Intramolecular SN2 reaction, forming an epoxide. Epoxides are basically more reactive than ethers because of the ring strain. Ethers are open chain, whereas ethylene oxide or epoxide has a ring strain, and because of that it becomes more active. These are ethyl ethers and this is ethylene oxide. So there is a difference in the stability and also the transition states. Excuse me. Ethers can undergo acid catalyzed mechanism. Epoxides, and the epoxide will open up. Okay, so this is your epoxide in the presence of an acid. Oxygen get protonated, become now protonated epoxide. Excuse me. So the incoming nucleophile, since this is a symmetrical epoxide, bromide can attack to either carbon, either to this carbon or this carbon. And then the epoxide will open up and forms the alcohol. Excuse me. What's this? Okay. And here's another instance. It's similar to the previous one. This is a butane, 4 carbon, and this is here you have ethylene oxide, and this is with 4 carbons, so your oxygen again get protonated. Symmetrical epoxide, methanol is the nucleophile. It can attack from either side, can either come to here or come here. Doesn't matter, it's symmetrical. And then a carbon-oxygen bond breaks and opens up the epoxide. And here you will find this oxygen attached to hydrogen as well as the methanol group that is attacking over here, attached to this oxygen. CH3 group right there, this is the methyl group. This oxygen right there is attacked into this carbon. Oxygen carries methyl group This oxygen carries the methyl group and the hydrogen. And the base comes and grabs this hydrogen. And we have alcohol and an ether group right there. Epoxides are more reactive than ethers, so the reaction easily occurs at room temperature. Epoxides will open its ring under acidic condition and under basic condition. Now this is what happened under acidic condition. Nucleophilic substitution, acidic condition. When you add HCl to epoxide, we know what's going to happen. Oxygen with the lone pair grab a proton from hydrochloric acid and make it protonated. That's what happened when you add HCl. And then you're going to react with methanol. Now methanol is going to act as a nucleophile, and it can go either to this carbon or it can go either to this carbon, methanol. Now this is not a symmetrical epoxide. So this carbon has two hydrogens and this carbon has hydrogen and a methyl group. And this has become the major product. So there are two possibilities. If the OH, this oxygen right there can either go to this carbon or it can go to this carbon. So that is how you get the two products. So the major product is this one and the minor product is this. Under acidic conditions, the nucleophile preferentially attacks the more substituted ring carbon. So which one is the more substituted ring? So this one right here is the more substituted one. This one. If the methanol attacks here, that would give you the major product. And then if it attacks here, it will give you the minor product. And then we will see in the next slide what is the reason for it to attack the more substituted carbon. Why the more substituted ring carbon? Now this is the intermediate that we had seen after the oxygen get protonated. Why methanol comes to this carbon? You see here this carbon-oxygen bond is going to break. Once the carbon-oxygen bond breaks, you are making a carbocation here. And this is a secondary carbocation that you are developing here. But if it goes to the other carbon, methanol goes to this carbon and oxygen bond is going to break and it is forming a primary carbocation. So secondary carbocation is more stable compared to the primary one. Because of that, under acidic condition, methanol goes to the carbon which has more substitution. Okay, and making it is the major product. If it goes to this carbon, this is the product it's going to form. So the oxygen carbon bond will break and it forms CH3, CHOH and CH2 and OCH3 group goes to this carbon to get this product. Okay, that's going to be the minor product. Nucleophilic substitution, neutral or basic conditions for epoxide. Earlier we had seen what's happening in acidic condition. Now this is nucleophilic substitution under nuclear or basic conditions. Now we don't have an acid to protonate the epoxide oxygen. So you have a nucleophile methoxide. So the methoxide nucleophile normally goes to the less hindered site. So this is a primary carbocation, this is secondary carbocation. So normally it goes to the less hindered carbon. This can also happen at a neutral condition too. If it is methanol, that would also go here. Okay, and this will open up. So CH3, CH, oxygen, and then the CH2 group will carry OCH3. And then when you add methanol or HCl, this oxide will grab a proton to complete the process. Picks up a proton from the solvent or from added acid. Under neutral or basic conditions, a nucleophile preferentially attacks the less sterically hindered ring carbon. These epoxides can be used in synthesis reactions. So this can act as a nucleophile. And then since it's a nucleophile happening under basic condition, it attacks less hindered carbon. And this carbon-oxygen bond will break. So this carbon goes and attack this carbon-oxygen bond opens up. This carbon-oxygen bond break. So you will have the product that you have right there, CH3 carbon, CH3 carbon, and then oxygen will be on this carbon, and it has this CH2, which is this one, and then the new carbon that's connected is this with the triple bonded carbon and methyl group. And when you add methanol, oxygen grab a proton from here and then complete the process. And in the second one, we have methylamine. Again, that is a base. That also going to go to the less hindered site. So methyl nitrogen goes to this carbon and open up the epoxide right there. So CH3CHO minus, CH3CHO minus, and this carbon attached to this nitrogen NH2CH3, and this additional proton will be lost to this oxygen, and then you have the final product. So I'll start the next section from here. We'll stop here for now.